Hi, I'm Thomas from Neuzeit Instruments, and this video is the official walkthrough of Orbit. Orbit is a great tool for sound design and can turn virtually any sound source into something new and exciting. In the first part of this video, I will explain each function step by step, and at the end of this video, I will do some sound samples and do some patches and explain what's going on in detail. On the website of Neuzeit Instruments, there's also a huge signal flow chart. I encourage you to open this document in addition to this video if you want to understand Orbit even deeper. So let's have a look at Orbit. The signal flows in a circle like this when you look at the device. We have audio inputs 1 and 2, which are amplified by these potentiometers. Their input level can also be controlled by external control voltages. The sum of both inputs passes through this one-knob bass equalizer, which raises or lowers the low frequencies. From here on, the signal splits into 3 paths. One path is called bleed and leads directly into the filter over here. Another path goes through the Bitcrusher section, and the third part goes through the Harmonics creator section. The Bitcrusher is called crush and the Harmonics creator is called harm. Both crush and harm generate unique harmonic waves that enrich the input signal and make it a sonically interesting waveform. How exactly crush and harm work is explained later in this video. The balance between bleed, crush and harm also defines the sound character of the generated voice. Therefore, before the signal paths enter the filter, their volume can be adjusted with this small mixer section here. The outputs of crush and harm are also available as separate sockets. The signal is tapped before their mixer potentiometers, so that they can be used externally and, if necessary, decoupled from the signal flow of Orbit by turning the corresponding potentiometer to 0. The filter itself is a 12 dB per octave voltage-controlled multimode filter, which allows simultaneous output of low pass, high pass and band pass. A special feature of the filter is that the fade potentiometer can be used to blend seamlessly between high pass and low pass. The fade parameter is also voltage controlled and has its own CV input. When the resonance is turned up to full, the filter starts to oscillate and produces a clear sine wave at the output. Of course, the cutoff frequency of the filter is also voltage controlled with 2 CV inputs, FRQ and FM. The frequency input sets the cutoff frequency with 1 volt per octave. The FM input has its own attenuator to multiply the control voltage by a positive or negative factor. The output of the filter shall be called the wet signal, while the unprocessed sum of input 1 and 2 shall be called dry signal. The volumes of dry and wet can be set with these potentiometers, whereby one input each is available for control voltages. Orbit also has its own envelope generator. The envelope can be switched between AD, AR and FLW modes, which denote attack decay, attack release and envelope follower. To adjust the rise and fall times of the envelope curve, these two potentiometers, AT and REL, are available. To trigger the AD and AR envelopes, there's an input socket for an external 5V trigger signal. The envelope is also available at the ENV output of Orbit with a voltage between 0 and 8 volts. The envelope is already internally routed to the cutoff frequency of the filter. The big env button serves as attenuator. In order to make the envelope audible, we feed a sawtooth oscillator into Orbit's filter and can hear now how the filter's cutoff frequency is modulated. The 2 LEDs on the left and right indicate how much and in which direction the cutoff frequency of the filter is influenced by the envelope. The external control voltages at the FM and FRQ inputs are also included in the LED display. For example, if we patch an external LFO into the FM input, the LEDs will indicate this. By using the attenuator of FM, we can control the influence of the control voltage in positive or negative direction. You can also set a mode in which the AD and AR envelopes repeatedly trigger themselves to form an LFO. Therefore, we access the secondary user layer of Orbit by long pressing the sync button. The sync button starts to flash now. In this user layer, the buttons have an alternative meaning where the envelope button sets the self-triggering of the envelope active or not. If the button is red, it means that the self-triggering of the envelope is active. We exit the secondary user layer by pressing Sync again. Our envelope is still in AD mode and has self-triggering activated now. In this mode, a signal at the trigger input resets the envelope to 0. If we change the envelope to AR mode, the envelope stops. It is only active as long as the trigger signal is high. It is worth noting that the envelope is generated by a 12-bit digital to analog converter, which also allows very short and precise envelopes. Most other stages of Orbit are completely analog, like the voltage-controlled filter and all signal mixes. Inputs 1 and 2 and the outputs dry and wet are also analog VCAs. Now let's take a closer look at the core functions of Orbit, Crush and Harm. We start with the Bitcrusher, whose controls are located in the upper left corner of Orbit. The Bitcrusher has some unique features that are not commonly seen on other Bitcrushers. To demonstrate this, we will use a sine wave as the input signal. So this is the dry signal, and this is the same signal going through the Bitcrusher. The filter is fully open and lets all frequencies pass through without affecting the sound. What the Bitcrusher is currently doing is read the analog audio input and translate it to a binary 12-bit representation consisting of ones and zeros. It then converts the binary representation back into an analog waveform. The conversion takes place within certain time intervals, and if the conversion rate is high enough, you do not hear much difference from the analog signal. Things start to change dramatically as soon as we lower the sampling rate by turning the rate potentiometer to the left. As you can see, we have added a ringing tone to the sine wave, which is the result of small steps that are introduced into the output waveform of the Bitcrusher. If we turn rate far to the left, the sample rate drops to about 100 Hz, so the resampled signal has only little to do with our sine wave. Now let's turn the sync knob on and turn the rate knob back so that the ringing tone forms an interval above the sine wave's frequency. With the sync button on, note what happens to the ringing tone when we change the pitch of the sine wave oscillator. The ringing tone still maintains the same interval relative to the pitch of the incoming signal, so we have practically added a second oscillation in addition to our sine wave oscillator. Playing a melody and changing the filter cutoff frequency by the envelope sounds like this. Okay, fine. So let's take a look at the next function of Crush, which adds some serious distortion to our signal. As mentioned before, the Bitcrusher basically reads an analog voltage, translates it into single bits, ones and zeros, and converts it back into an analog signal. Now we can force Crush to deliberately make some translation errors. To do this, Crush has these 4 buttons at the top that allow you to change the behavior of individual bits of the digital to analog conversion. The button on the far left affects the most significant bit, bit number 1. The next button affects the second most significant bit, bit number 2. This button, bit number 3, and bit number 4. If we now tap a button, it switches off and lets the Bitcrusher always translate the corresponding bit to 0, no matter if it was read as 1 or 0. If we press the button again, it turns red and shows us that Crush now inverts the bit. This means that if Crush originally read a 0, the bit is converted to a 1 and vice versa. By changing several buttons, we can adjust the distortion to our own taste. To better understand what is going on inside Crush, let's have a look at this graphic. Orbit reads the incoming analog signal and converts it into its binary representation consisting of 12 bits, which can be 1 or 0. Now we can force Orbit to intentionally make some bit translation errors. In terms of sound, this introduces harmonics that are multiples of the fundamental frequency of the incoming signal. You can force translation errors with the 4 top buttons of Crush as follows. A red button inverts the bit by translating a 0 into a 1 and a 1 into a 0. A dark button will always translate the bit to 0 even if it is originally a 1. A blue button means that the bit is translated normally and not changed at all. You will notice that bit 1, the most significant bit, or short MSB, has the greatest influence on the sound, while the further we move to the least significant bit, LSB, the less the signal is affected. With Orbit, you can also change the behavior of its parts by accessing a secondary user layer. To do this, you must press and hold the sync button for a short time. Now, the buttons have a different meaning and allow you to change the behavior of Crush, Harm and Envelope. The 2 buttons on the right have an effect on the behavior of Crush. The second button from the right changes the bits affected by muting or inverting. The translation with alternative settings now looks like this. While the default behavior is bits 1, 2, 3 and 4, the alternative setting is bits 2, 3, 4 and 5 and 6 and 7 and 8 at once. Thus, the possibilities of distortions simply become more varied, and it is also possible to change the less significant bits 5 to 8. Let's check out the difference here. This is our sample with different types of distortion in normal bit mode and with the alternative bit setting. This graph is intended to help you better understand how a single bit affects the output waveform in Crush. Suppose our audio input is a sawtooth. Bit 1 changes its state only once per waveform cycle, bit 2 changes twice, bit 3 changes 4 times, and so on. A bit can only have 2 states, which are called 0 or 1. When reconstructing an analog value from the bit representation, the values of the bits have different weights. For example, the amplitude of bit 2 is half the amplitude of bit 1, the amplitude of bit 3 is half the amplitude of bit 2, and so on. If we add around the output amplitudes of the bits, we get something that looks more and more like the original sawtooth the more bits we add. With 12 bits resolution, we get a sawtooth wave with 4096 steps, and with 8 bits, we get only 256 steps. This is how the sum waveform of bit 1 and 2 from our example change when we invert bit 2. In the frequency spectrum, this produces overtones, which are however integer multiples of the fundamental frequency. By activating all bits and inverting only a single bit, we get our sawtooth, which is distorted with some steps. We are again in the secondary user layer now. The button on the far right changes Crush from 12-bit mode to 8-bit mode. In our translation graphic, the change from 12 to 8 bits makes the translation look like this. The least significant bits are simply ignored. The difference in sound between 12-bit and 8-bit is most noticeable in soft tones or tones that fade in or fade out slowly. With 8-bit, you always have a slight noise because the resolution of the quiet parts is not as high. While in the alternative user layer, the rate LED also has different meaning. It now shows us if the input signal of Crush is clipping. While clipping should be avoided on many audio devices, clipping on Orbit mainly means that all bits of the Bitcrusher are used. Distortions occur anyway in the Crush section and are also the primary goal of Orbit. Operating Orbit with clipping can be seen just as another tool for sound shaping. So far for bit crushing. Now let's check out Harm, the harmonics generator. Harm works in parallel to Crush and follows a different philosophy for adding useful harmonic content to the audio input. Harm and Crush can complement each other very well when mixed together. The core of Harm are 5 square wave and noise oscillators, each with its own volume potentiometer. Each oscillator has a different pitch, but thanks to the pitch analysis of Orbit, it can follow the fundamental frequency of the input signal. The 5 oscillators are marked with dots and squares. Let us start with dot 1. Dot 1 is always a square wave that acts as a sub-oscillator and is 1 octave lower than the input signal. This allows us to extend the input signal by additional bass frequencies. Here you hear a sawtooth waveform as the input signal. Now we add dot 1 as an additional oscillator. Dot 2 also outputs a square wave that corresponds to the bass frequency of the input signal, while dot 3 outputs a square wave that is 1 octave above the bass frequency. By mixing all the oscillators dot 1, 2 and 3 to the input signal, we can emphasize the fundamental frequency of the input signal or add the octave above or below it. Listen how the oscillators of Harm follow the pitch of the input signal. The square 1 and square 2 oscillators are also pulse waves, which are 1 octave apart, but we can add a frequency difference relative to the fundamental frequency of the input signal. For this we use a potentiometer delta F. This is our input signal again, the pure sawtooth wave. Now we add square 1 while delta F is in its center position. The frequency of square 1 corresponds to the fundamental frequency of the sawtooth signal, but if we turn delta F to the right, the frequency of square 1 increases. If we turn delta F to the left, the frequency of square 1 decreases. Delta F has a control range of plus minus 1 octave relative to the fundamental frequency of the input signal. If I set delta F like this, we have formed a fifth interval. No matter how I vary the pitch of the input signal, the interval remains the same. By adding square 2, we add another oscillator, which is 1 octave above square 1, and thus make our signal even richer in overtones. Together with the oscillators dot 1, 2 and 3, we can now build rich chords around the input signal. These chords will always follow the fundamental frequency of the input signal. Of course, there are also alternative settings for the Harm section. If we go to the secondary user interface, the leftmost button can be used to change the behavior of square 1 and 2. If the button lights up red, the so-called hard sync function is activated for square 1 and 2. This means that the input signal acts as a master, and after each cycle of the incoming waveform, the amplitude and phase of the square oscillators are reset. With hard sync, you can create timbres that sound more cutting and metallic. The core of the hard sync function is the detection of zero crossings from negative to positive amplitude of the input signal. The time interval between two zero crossings is also used to determine the fundamental frequency of the input signal. This algorithm has the advantage that the harm oscillators instantly follow every frequency change of the input signal. However, with this method it is no longer possible to determine the fundamental frequency of complex waveforms. But alternative settings of Orbit offer us the possibility to use the harm oscillators in a cool way anyways. Push the most left button in the secondary user interface so it gets dark. This means that square 1 and square 2 no longer follow the measured frequency of the input signal at all. With delta F we can now set them to a fixed frequency. To show this in a sound example, we choose a drum loop. By setting delta F accordingly, we can emphasize the bass of the kick drum. If we now modulate the cutoff frequency of the filter, in this case set to low pass, we can create an additional bass line. There is another alternative setting which affects the dot oscillators. By pressing the second button from the left in the secondary user level, dot 2 and 3 become noise generators. The noise of dot 2 sounds more lo-fi. Our drum loop example can now be enriched in many ways. We first turn on the dry signal to get the full punch of the drums. Then the wet knob lets us add the harmonics of harm just as we like. Let's see what we can get out of the simple drum loop with both enabled harm and crush. I have also added an external envelope trigger. In this patch we investigate the processing of chords. Chords are complex sounds, which means that Orbit will not be able to track the pitch correctly. Anyway, we will have fun here. I will guide you step by step through the patch you're listening to, just from the beginning. On the left side we have a converter that converts a MIDI sequence into CV and gate. The CV is routed to the microbraids oscillator that generates the chords. The output of microbraids then goes into Orbit's input 1. The output of Orbit passes through the Pico effect on the right side, which adds a little delay. I will now show you the output of Crush, Harm and Bleed separately so you can see how the sound is composed. This is the pure oscillator sound that goes through the Bitcrusher of Orbit. The bit translation is all set to normal, which you can see by the blue buttons, but the rate is set to a middle position. This means the rate is roughly in the range of the audio frequencies. The first trick is to connect the CV of my sequencer to the rate input of Orbit. The scale control of the rate CV is set to a positive value. This means that rate is modulated by the pitch of the chord. To make it sound less sharp, I simply turn down the filter cutoff frequency and modulate it with the internal envelope of Orbit. So I connect the trigger signal from the sequencer to the envelope's trig input, and the envelope, which is set to attack decay mode, is triggered. The envelope potentiometer adjusts the amount of internal routing to the cutoff frequency. If I now change rate again, it starts to sound bell-like. By going to the secondary control level, I can turn on the envelope self-triggering. Attack and decay are set so that the timing of the envelope matches the BPM of the sequence. Also, if there is no trigger getting in, the envelope sometimes triggers itself. Let's see how the output of Harm sounds. I turn Crush down and turn Harm up. When I go to the secondary user layer, I see that the leftmost key is off, which means that the square 1 and 2 oscillators do not follow the pitch at all. The pitch is only set by delta F. I set delta F so that it matches the pitch of the chord sequence. To do this, I listen to the dry signal. By setting the second knob red, the oscillators dot 2 and 3 are put into noise mode. This is the noise of dot 3 and that of dot 2. The dot 1 oscillator still tries to follow the pitch, and in this case we get these dirty little glitch noises. Sometimes bass EQ has some influence on the pitch tracking, but not so much here. Together with the square oscillators, it sounds pretty edgy. I now try to find a nice balance of the loudness of the individual elements. When I add crush, this adds up pretty well. Let's also add some delay just for fun. This is now another little trick to connect the envelope of Orbit to the wet CV input. When I do that, I can turn wet off completely and the envelope alone now determines the output volume. Let's also use the fade parameter. When I turn fade to the right, the high pass is faded in. I use the internal envelope to automate the fade parameter, but with this nice little tool here I will scale the envelope to a different range. With my little scale tool I invert the envelope with the second potentiometer from above. The fade CV input takes voltages between 0 and 5 volts. By also adding a positive DC offset with the upper potentiometer, I make sure that the envelope now goes from minus something to plus something volts. But since fade only senses voltages greater than 0 volts, fade remains fully turned to low pass as long as the fade CV is negative. Only after a short time, as soon as the CV becomes positive, it starts to fade into high pass. So this effect is nicely delayed and now sounds like this. Finally, let's automate the cutoff frequency by adding a slow LFO to the FM input. The LFO signal comes from peaks and the FM attenuator is set to a slightly positive value. This is quite straightforward. Note that the LED on the left of the envelope knob now sometimes turns on when the LFO has a negative voltage. I'll finally just play around with the parameters a bit and try to find some nice sweet spots. Also here, let's just add some delay.